Okay. Today we are happy to have Xiang from Argonne National Lab, and Xiang is a postdoc in Argonne. He graduated in USTC in China in 2017 and did his PhD in, from Tsinghua University in 2021. And then he visited Brookhaven National Lab and engaged research in high structures for lattice calculation. And he joined CCNU in 2021 to 2022. And now he is a postdoc in Argonne University. He is interested in the internal structure of hadrons from lattice testing. Today he will give us about pattern distribution from boosted field in the Coulomb gauge. Yeah, please.
Okay, thank you for the introduction and thanks for the opportunity to present our work. Today I'm going to briefly discuss about the pattern distribution from lattice QED using the boost field in the Coulomb gauge. Okay, so here is the outline of my talk. So firstly, I will give a brief introduction of pattern distributions and how to compute them from the framework of lattice momentum effect theory. And then I will discuss the universality of LaMET. And next, I will introduce the pattern distribution from the Coulomb gauge corrrelators. And finally, I will give you a summary. Okay, so why we are interested in the hadron structure and the pattern distributions. So after Big Bang, especially since the formation of protons and neutrons, they constitute 99% of the mass of the visible universe. Then the nature question, of course, that where does the mass come from? Now we know that in the standard model, the Higgs boson is responsible for giving the elementary particles their mass, but that only explains a small fraction of the proton mass. For example, these 3 current quarks only contribute a few MeV to the 1 GeV proton mass. So the question is, where does the rest of the mass come from? It turns out that the neutron is not simply consisting of 3 current quarks. It is instead a relativistic system of the fast-moving quarks and gluons. And the neutron mass should come from the relativistic motion and strong interactions among the quarks and gluons, which can be described by the quantum chromodynamics. But it's still very puzzling to us how does it happen. There are still questions about how the quarks and gluons distributed in the nucleon and where does the neutron spin come from, and what is the 3-dimensional imaging of the neutron structure. All these questions are highlighted in the long-range plan, and we would like to understand them. So to understand these questions, we need to build the hand scattering facilities, such as applying the electron ion collider at Brookhaven National Lab, where we boost both electron and the neutron to the speed of light, which allows a large momentum transfer within their scattering, so that the scattering cross sections can be vectorized into the convolution of these non-perturbative pattern distributions, and the perturbative Hart processes, which describe the electron quark scattering. This way, we can define a multi-dimensional imaging of the neutron. Describes the possibility to find a pattern carrying a momentum fraction x, as well as transverse momentum kt and transverse position bt. All this information can define the so-called weakness distributions, or separately encoded in the transverse momentum dependent distributions, and the impact parameter distribution. The Fourier transform of the later one is the Fourier transform of the so-called generalized pattern distributions. And if we integrate over all the transverse information, we will get simplest but the most important one-dimensional pattern distribution functions. And all these functions are non-perturbative quantities because the quarks and the gluons are confined inside the neutron. So that one may expect that we can use the non-perturbative lattice calculation to calculate this quantity and help us to understand the hadron structure. However, this is not so straightforward because the Parton distributions are usually defined as the Fourier transform of lattice correlations, where for example, the quark field are separated along with the lattice direction, so that they are real-time quantities and cannot be directly simulated on the Euclidean lattice as a SAM problem. So we need a good idea to bypass this issue. Then it was proposed about 10 years ago that we can instead compute the so-called quasi-distribution from the equal time correlators, where we use the operator, the quasi-PDF operator, used with the form very similar to the lattice case, but now the quark field is separated along with the spatial direction, but equal time. Then you can do. Then it requires external hadron state to have a very large momentum. Then in the hadron rest frame, the operator will be boosted close to the lattice. And in principle, if you have an infinite large momentum, then you directly get the lattice PDF or TPDs. So it's large by the finite momentum. The difference between this quasi distribution and lattice distribution is supposed can be compensated by the perturbative factorization formula. That is, we do a large moment expansion of the quasi distributions, for example, the quasi PDFs. To be specific, you can calculate do the perturbative calculation of the quasi distributions and the lattice distributions. And order we should find that their IR physics must cancel or their collinear divergence must cancel, so that their difference is only UV difference, and it can be compensated by a perturbative hard kernel up to the power corrections suppressed by the large momentum. This so that we have, with this formalism, we have a factorization formula very similar to the DIS or Xiang, and have directly sensitive to the X dependence of the Parton distributions, and to improve the prediction power of this approach, the large momentum is a key for this approach. And literally, it has been shown that this formalism also works for the TMD case, where the quarks, you have the quark not also separated with transverse spatial direction, and connect them by a stable shape loop. Then you use large momentum boost to boost it to the lattice TMD. So in the past few years, within under the framework of the large momentum effect theory, there have been many progress. For example, we computed the pion valence quark PDF, and for the first time used the two-loop perturbative matching kernel and extrapolation to the continuum limit. Our result shown as the red line here is the independent QCD prediction from lattice QCD, and it appeared to agree with the global analysis of the experimental data, like the Xiang global analysis result. The agreement is very encouraging and motivate us to expand our studies towards, for example, the three-dimensional GPDs from the LaMET. For example, recently we computed the pion quark GPDs with multiple three-dimensional pion quark GPDs with multiple value of moment transfer T, and we are also keep improving our systematics, including the two matching, the renormalization group resummation, and as well as the leading renormal resummation and subtraction.
A question.
Sure.
So how do you usually do boosting numerically? Or
boosting?
Yeah.
So the hadron state you can have momentum on the lattice, right?
Yes. So you simply add the phase factors to the interpolating operator? Or?
No, you just compute the hadron, large momentum hadron state matrix elements.
Okay.
Then that is equivalent to, if you look at them in the hadron rest frame, the operator will be equivalent to this close to that.
Oh, okay.
You don't have to do anything.
Okay.
To make that.
Go back to the previous slide. You compared to jam. I'm going to make sure I understand what you're showing here. So this is valence quark.
Right.
FV. Okay. And so the red is your lattice calculation, and then jam is now some global fit to data,
Yeah, right.
and it's got too many curves there. Which is gem? The black. It's got some like a central value, and just trying to find out which is which.
Oh yeah. So this is our recent calculation, and this is one is older calculation. The gem is the black band here. Central value is here.
Okay, so it's pretty much overlaps your calculation.
Yeah, right. Yeah. The rest are some older global analysis.
And okay, so the big one is the big plot is F, and the small one is scaled by X.
X times.
That's impressive. Is that maybe I haven't been paying attention? Is that new?
Yeah. So it's very impressive for the pion, because for pion both the experiment also don't have a very good determination, so they have this kind of errors. So our lattice have a slightly larger error but compatible. But for the case of nucleon, the nucleon PDF are very well measured. The error is tiny. So in that case, the lattice QTD is not as well as the experiment.
Have you done nucleon?
We have done nucleon. The error is much larger than the experimental analysis.
I'm happy with that. It's consistent.
Yes.
So also at the x to the 1, x to the 1 is still not 0 yet, right?
X to the 1. We don't have we don't have control of x to the 1 and x to the 0 region because of the power corrections. We only have this middle range.
So the upper delicate ion, the red one is pretty far from 0, right?
Oh yeah, right. Because it's power corrections. It should be in principle it should be decayed to 0, but we don't have control of this region.
So simple reason why you're only doing valence. Can you do strange? Can you do super?
We can do strange quark. So there are two. In principle, we can do that. The complexity is only the computational effort. So the C quark have word signal, and because they are disconnected diagrams on the lattice, they have word signal, and they also have mixing with the gluon because when you do the decay evolution or something like that. So you really have to compute all the C quarks and gluons together to have a very well controlled syntax.
Now, what does it mean for this to be valence quarks only? Does this just mean that you ignore disconnected contributions to these correlators?
Right.
But that's not the same as saying that this is like a valence quark.
The valence quark is
right?
U minus U bars, D minus D bar, right? It's with as being symmetry. If you use the as being symmetry, the U minus U bar is equivalent to the U minus D, which is that vector on the lattice, and it don't have mixing with the gluon, so that it can be separately calculated.
Okay. All right.
One question more about the continuum limit there. So how many lattice spaces do you have there?
It's roughly a continuum limit. It only has to consist of two lattice spaces.
Yeah, but also, there is a problem because you need P set to be large in order for the power corrections to be small.
Yeah.
But at the same time, you need P set to be small because if not, the lattice artifacts are very large. So you have this kind of two-scale problem. And,
yes, the momentum should be smaller than the lattice cutoff. So generally, for example, in this calculation, our largest lattice cutoff is 5 GeV about. What's 5 GeV? It's 0.04 for me lattice. So that and our momentum here is 2.4 GeV. So it's still safe.
So 4 GeV is the finest lattice.
Yes, the
other one is 3.2.
The other one is 3.2. Yes. Let me continue. So, we are computing the pion quark GPDs with multiple value of t, and we are also improving the systematics, including the two-loop matching and the renormalized group resummation and the leading renormalized resummation subtraction. And from these quark GPDs, we can do the Fourier transform to derive the impact for matter distributions, as you can see from here, and you can observe quantitatively that when for the small s case, the distribution the quarks have a broader distribution, where for the larger s For the quarks with larger x dependent, they are more centralized. So there have been many progresses in recent years, but there are still many difficulties and complexities in computing these Parton distributions. One of the complexities is the renormalization. That luckily we know that for this non-local operator connected by a raised line, it can be multiplicatively renormalized by linear divergence comes from the Wilson line self-energy, and the logarithm divergence is the overall constant. The dA is very easy to deal with, but the linear divergence, we need to subtract them. For example, the so-called self-renormalization or static potential renormalization, they basically extract the delta M from either the hadron matrix elements or the Wilson loop. Just extract the delta M from the Wilson loop and subtract them from the barometric elements. But those are all lattice non-perturbative renormalization scheme, and we need to match them to the MS bar, commonly used MS bar scheme. And to do so, you will encounter renormal ambiguity when you determine this delta M. And to solve this problem, if we do not solve this problem, it will introduce the linear power fraction in the factorization. And to remove this linear renormal, we need to do a linear renormal resummation and really subtract them from the matrix elements. Then the complexities in the lattice simulation, as mentioned, that the momentum is the key to surprise the power fractions in both small x and large x. But it is very difficult to increase the momentum and on the lattice with a good precision, because the signal, on the one hand, the signal will decay exponentially as the momentum or the energy increases, and meanwhile the signal also decreases very fast when the separation between the quark pairs, anti-quark operator becomes large. So the long-range data are very noisy. So we are difficult to move to large momentum and large separation. And that issue is more problematic for the TMD case, because the TMD, you have a very long stable shift Wilson link, which is the length of the Wilson link is 2 lengths of these legs, and plus the transverse link, which is much lesser than their longitudinal separation. So this geometry also further complicated the renormalization due to the operator mixing and the pinball singularity, task singularity, something like that. It also caused rapid error growth. For example, this is the Collins-Soper kernel, or the rapidity evolution kernel for the TMD extracted from quasi-TMD approach, and you can observe when the transverse separation grows, the errors increase dramatically. So we don't really have, we cannot really have good control in the large BT region or the deep unobserved region, which is of more interest. So of course, on the one hand, we can put more resources and more effort to increase the precision and improve the systematics. But on the other hand, we also may also think.
Maybe just since I don't know anything about this stuff, I mean, why is the large BT region of interest? Like what's phenomenologically?
Because at a short distance, you can use a perturbation PQCD coverage, right? UV, but when the B perp are larger and larger, it's not perturbed region. Usually, if you want to extract from experimental data, or you can use some factorization to fit the data, but you cannot use PQCD calculator.
Okay, well, maybe just to ask another super question, I mean, why do you want to do that other than it's hard?
Because when you want to have the TMD, which for the TMD distribution, you want to do a Fourier transform of B perp and have the transverse momentum KT, and it's more interest when the KT is small, gotcha. Which is the long BT region. When KT is small, it's a confined motion inside the waveform, it's small confined motion. So we may also think of some other approaches to think about how to bypass this kind of issue. That is the next part of this talk, is the universality of LaMET. So let's look at again this common operator used in both quasi-PDF case and the lattice PDF case, where you have the non-local operator separate in some direction. And to have this non-local operator meaningful in the gauge theory, you have to attach the quarks field by a phase, which is a linear function of the in nu. And in the DIS, the field of a quark is actually you have the quark and you have a Wilson line connected and extended to infinity in the lattice direction, which can be written in this way. So that if you combine the anti-quark operator together, their two links will cancel and only leave you with this Wilson link, lattice Wilson link connects them. So this lattice operator this lattice operator is equivalent to the case of the free quarks inside the lattice gauge, where you stack the A plastic simply equals to 0. Simply equals to 0. So then we can use the same language to understand the lattice momentum effect theory. That is, we have two quarks separate along with spatial direction and connected by a Wilson link AZ. Then it is equivalent to the free quarks in the actual gauge when you set the AZ equals 0. And the Lorentz boost, the lattice momentum boost to the lattice PDF is that you boost the free quark in the actual gauge to the lattice as well as boost the actual gauge AZ equals 0 to the A plus equals 0. So in this language, so we may think that that besides this actual gauge, we can choose any physical gauge and use a free quark in this physical gauge, like the temporal gauge is 0 equals 0, or the Coulomb gauge. In this case, we fix the gauge, we write down the two quarks with the spatial separation, we boost it to the lattice, either for the quasi-PDFs or the quasi-TMD when you have a transverse separation. So what we are thinking is that we may consider compute the Parton distribution from the Coulomb gauge quasi-distribution operator. But the question is that this is our our thinking, and the question is that this really works in real work, does the factorization really works, and is there any advantage that we use the Coulomb gauge instead of the actual gauge? Can they simplify the renormalization? Can they have better long-range precision?
Question. So why Coulomb gauge is chosen here?
So why the Coulomb gauge is chosen here? There are many gauges, but the first ones coming to our mind is AZ equals 0 gauge and temporal gauge and Coulomb gauge. AZ gauge is commonly used gauge-invariant, we call it PF already. But A0 gauge, it could have the same issue as AZ gauge. It could have linear divergence. But it's generally you would think they are similar. And the Coulomb gauge could have some different features. We will discuss later. So firstly, we do the probability calculation of this quasi-PDF in the Coulomb gauge, and we find the collinear divergence are identical between the quasi distribution and the lattice distribution.
So can you go back, try to expand us again? What's the advantage of using Coulomb gauge instead of the other gauge, like physical gauge or?
So there. The physical gauge here, you have many choices of physical gauge as long as the physical gauge here we define is as long as when you boost the momentum, the gauge condition will be boosted to the lattice gauge. So that includes the actual gauge, temporal gauge, and Coulomb gauge. the AZ gauge, we know there is linear divergence because if you write it in it's equivalent to the gauge-invariant quasi-TMD, right? So AZ, you either set is equal to 0 or it is straight with line along.
That's all technical. I mean that divergence is difficult to
that divergence is why we want to find another way to compute it. That divergence causes the complexity in the renormalization as well as ladder errors.
Yeah, I mean divergence is just part of the renormalization, but you can eventually to absorb into some other part of the operator.
Yes. So, but that's the renormalization. Yeah, if you do that, as we said, will be a linear renormal that you need to subtract in the linear divergence. And I will show later that when you subtract the linear divergence, that will enhance the noise in the long-range data. So that's something we want to improve here. So in principle, all of them are equivalent. Eventually, if you have an infinitely large momentum boost, all this will give you less PDF. So
what?
Eventually, if we have an infinitely large momentum boost, all the gates here will give us the less PDF. So they are in the same universality class of the LaMET. So in the large moment limit, they are the same. So we are trying to find which one have some advantage in some situation. Yeah.
Numerical advantage.
Yes, numerical.
So if you want to do this numerically, do you have a problem with Gribov ambiguities and this kind of fixing the gauge?
I will mention that, but I can see here. Yes, when you fix the Coulomb gauge on the lattice, now observatively there will be Gribov copies. Could be Gribov. No, there is Gribov copies. Question is that if that will influence our measurements, and if that is a significant issue, then when you increase the number of configurations, the error will not reduce because the Gribov copy will exist like a systematic error. They are different gauge of it. They will never. They are not the same. So that when you increase.
Or maybe numerically you are falling in the same. In the same place for the Gribov copies, but you are missing some other configuration.
Right. So
I mean, the statement in principle is that non-perturbatively you cannot fix these gauges.
In non-perturbatively, yeah, you have the Gribov copy. They are equivalent copies, and we currently we don't have this visible issue, but we also have a ongoing project to study the Gribov copies.
I should mention that maybe somebody else knows. You can fix the gauge, axial gauge, Coulomb gauge on the lattice, but there's no algorithm to fix the time gauge, the timeline gauge.
This one?
On the lattice.
Temporal.
Temporal lattice.
Temporal
we tried it and then nothing worked.
Okay.
Because we'd like to have, the thing is we did the gluon, boosting all this to the infinite momentum frame, then you becomes gauge invariant. We tried it that with the Coulomb gauge to calculate the glue spin some time ago. And that Coulomb gauge, the perturbative factor, the LaMET factor is huge, just cannot be used. And then the timeline, the temporal gauge will have no correction first order, but there's no lattice formulation unless somebody else knows. There's no time. We tried it with Polyakov gauge and so on, and it didn't seem to work. So there's no really good temporal gauge fixing on the lattice. What I was trying to say.
Okay.
Yeah, that's something which is not.
Okay, then we are lucky
necessarily. We're just saying that.
Okay, then we are lucky within the first.
We have not been able to solve.
Okay. Yeah. Okay.
Yeah, it's not related to your work. Sorry.
Yeah. Right. So we first checked in the perturbative calculation that the collinear divergence, the analytical and cancel, the difference between the Coulomb gauge quasi-PDF and the lattice PDF is only the UV perturbative matching kernel. And the matching kernel also studied by the particle number conservation. Then we move on to some real lattice simulations, so some key features and something we concerned in this. So we do this lattice simulation again for the pion valence quark PDF, and for both gauge-invariant case, whereas quark connected by a Wilson line, and the Coulomb gate case without a Wilson line but fixed in the Coulomb gate. And here is our lattice setup for this test. And the first feature we want to show is that for the gauge-invariant case, we know that we need to have a straight Wilson line, and the straight Wilson line can only be on the axis. This direction, it cannot be of the diagonal directions, something like that. But for the Coulomb gate without a Wilson line, you can put the quark field on any direction, and you can get this. You should be able to get the same quasi distribution as long as the momentum and the spatial separation are along the same direction. And as you can see from here, we have the z along the n-axis direction and the diagonal direction. So the parameter elements overlap with each other very well. For the larger momentum case, we don't have precisely the same momentum, but still they have very good agreement. That means the Coulomb gauge matrix elements precisely preserve the three-dimensional rotation symmetry. This is only a small feature. Then the most important thing is if this matrix element can be properly renormalized. So first of all, we know that the Coulomb gauge QCD can be renormalized. And there has been some studies of the quark propagators in the Coulomb gauge, and it shows that it can be multiplicated. Propagators can already be multiplicatively normalized. So we expect there will be no linear divergence for this Coulomb gauge operator since there's no Wilson line, and the renormalization is overall constant without a linear divergence, and it is independent of z. If this is true, then the matrix elements can be, we can use any matrix element from any z to construct a ratio and cancel the UV divergence, so that you use a different, choose a z, put it in the denominator, and construct the ratio. The ratio of the parametric elements should be the same as the ratio of the renormalized matrix elements without the dependence of lattice cutoff. And to see this, we use two lattice with fine lattice spacings 0.04 and 0.06, and we use the ZS in the same physical unit, and we choose two different ZS to show this. And it's, as you can see, the result from two different lattice spacings precisely overlap with each other, and show you excellent continuum limit, except the first view point of view where you have discretization effects. That means that indeed the Coulomb gauge parametric elements can be multiplicatively normalized by an overall constant, and is independent of z. Then we do a direct comparison between the renormalized matrix element between the gauge-invariant case and the Coulomb gauge case. And for this case, we use a so-called hybrid renormalization scheme, which is at a short distance, you use matrix elements with different momentum at the same z to cancel all the UV divergences. But for the long distance, the denominator is fixed at a short distance value. And for the gauge-invariant case, we need to further remove the linear divergence and the renormalon in the linear divergence, which depends on z. And this factor is exponentially enhanced factor. It's enhanced both the signal as well as the errors. So that's the issue we have mentioned, that for the gauge-invariant matrix element at long distance, the errors shown at the red data point are huge. Where for the Coulomb gauge case, there's no need to subtract the data and not. It's simply this ratio, and so that the yellow data point shown here have very good signal in the long distance, and it's smoothly converted to zero at long distance. That's the good feature we want to observe from the Coulomb gauge case, which can improve our calculation.
Sorry, so the plot is just the two ratios, right? What is the y-axis for the plot?
This quantity.
Okay, so for the GI case, you plot the first you use this first ratio, and for
the two ratios, right? It's a piecewise function and like 0.3 for me usually.
Oh, okay.
0.3 for me. For smaller than 0.3, this is the ratio. For larger than 0.3 for me, the denominator we cannot use larger z, and for the gauge-invariant case, we just need to separately subtract the linear divergences.
So in principle, you plot the same thing for the two cases.
Yeah.
Okay.
Right.
Here.
Yeah, but for the Coulomb gauge case, you don't have this factor.
Okay. Yes.
Can I also ask a very dumb question from a non-theorist? Like, when plotting these two approaches, how does one interpret? For example, I can see the errors are getting smaller, but I can also see like areas where the points don't agree with each other, like even within the errors. Like, what does it mean about the errors?
So by definition, it should be different.
Okay.
We'll just I'm just going to show that. So by definition, at finite momentum, the gauge-invariant definition or Coulomb gauge definition, they have different. They approach the lattice differently. So they have different power corrections. So that's a very good question. So at finite momentum, you can observe difference as already observed in the matrix elements case. When you do the Fourier transform, the quasi-PDFs also have different are also different as a dashed bands. But after the matching, the resulted lattice PDF shown the solid bands agree with each other in the middle range of X. This demonstrating that in the lattice momentum limit, the Coulomb gauge and the gauge-invariant case fall into the same universality class in the LaMET. So,
I think you're like zoomed in. I think it was something that you touched on the screen. Yes.
Just
Right.
double tap.
That's okay.
Still. Okay, so then let's do a point-to-point comparison between the gauge-invariant case and the Coulomb gauge approaches. So, firstly, the Coulomb gauge case, you don't have a written line. You can choose any direction of quark separation, any direction of momentum. It's not so important. And for renormalization, compared to the Coulomb gauge case, the gauge-invariant case need a linear to remove the linear divergence as well as the renormal ambiguity, the associated renormal ambiguity. After you do the renormal ambiguity subtraction, they will end up. They both have the quadratic power correction in the momentum. Then there are also drawbacks of the Coulomb gauge case, as already mentioned, the possible grid-up copy, which may affect the long-range region because you cannot do a perturbative. So the Coulomb gauge condition is usually a perturbative condition. When the non-perturbative value, you may have different copies within the same gauge condition. So that may affect the long-range region. But so far it's not visible in our calculation, and we have an ongoing project to further study this issue. And since the Coulomb gauge case breaks the Lorentz symmetry in certain cases, due to the breaking of the Lorentz symmetry, it could have operator mixings, such as when you do the OPE of the Coulomb gauge operator. And the higher order, the perturbative corrections, like for the gauge-invariant case, we have the two-loop available. But for the Coulomb gauge case, we only have the one-loop matching kernel for now, and it might be harder to go beyond one loop. But the important feature we want to see, and we actually see, is that the absence of linear divergence will greatly simplify the renormalization and also enhance the long-range precision, so that it could have broader use in the future, particularly in the TMD physics. Okay, then let's go to my last part. So as an example, we compute the pion TMD wave function. Just a brief idea, the pion TMD wave function describes the overlap between the pion state with its leading Fock state with the quark and with two quarks, and the two quarks carrying momentum fraction x and y minus x, and have a transverse momentum. On the lattice, we compute this kind of operator, and for the gauge-invariant definition, have a very long statistical-shaped reasoning. For the Coulomb gauge definition, we only have the spatial separation both in longitudinal direction and the transverse direction, but without reasoning. So,
can I ask you some questions? I thought people in a similar context, you get a very long stable type of scheduling that will signal the final state interaction. The final state interaction. And also if we can take a straight line, that gives you the G, like orbital angular momentum.
Yeah, right.
And these two are different because the other one has a final state interaction, this one doesn't have it.
Yeah, that's
so the Coulomb gauge, you mean you cannot distinguish these two cases anymore?
No, the Coulomb gauge actually can distinguish them. So the Coulomb gauge, what the Coulomb gauge do is that you have it goes to the very beginning. So in the lattice gauge, you have in lattice gauge the quark field is attached by a reasoning to infinity, right? And for the TMD, you have two quarks separated in both longitudinal direction and both in lattice direction as well as transverse direction. So you have two gauge link to the infinity, and they connected in the infinity direction, right? Connected in the infinity. And the Coulomb gauge method is that we put the Coulomb gauge here with this gauge factor, and after infinite lattice momentum, this gauge factor will become the lattice gauge factor. So so when we boost the Coulomb gauge TMD, it will precisely give us the stable shaped TMD instead of the straight TMD. Yeah, so because the gauge link is boosted to the lattice gauge link, and the two quarks, if you have the transverse separation, they will have two links to infinity. Yeah, then let me directly show you the renormalized quasi-TMD wave function matrix elements from the Coulomb gauge case as well as the gauge-invariant case. As you can observe, the Coulomb gauge that are shown as solid, the field square data point, they have very good signal here, and they even at start Z and light Z and small BT and large BT. But for the gauge-invariant case, the signal is fine for the smaller BT, but when you use the BT, the signal dramatically becomes very disaster. You cannot get anything, for example, from the BT in perturbation case 8A, shown as the gray data points. And well, the Coulomb gauge case have a very good signal and smoothly decay to zero when the BZ becomes large, so that we can do a very stable Fourier transform to get the.
You're also not much, even in Coulomb gauge, they are not much dependent on the
BT
transverse
separation.
Yeah.
That's not so strong.
What?
Dependence. Dependence is not strong, right?
It's almost large BZ is almost independent,
right? Right. Yeah. So.
Is that expected?
No, it's not. So we don't know the reason, but it's appear to be so. I don't have a very sensitivity to the BT, but it will capture the correct TMD physics, and I will show later. I will show later. So, so basically here is the small z is a little bit smaller, but a large BZ is actually a little bit higher. But it's not because the scale is large, you cannot really see it. The scale is to adjust to show the
I know, you try to show the different gauge,
Yeah.
At least the advantage of Coulomb gauge is have small error bar at least.
Yeah.
Converge, but
right.
Just wondering, curious why it does not depend on your saturation, the impact parameter be perfect.
It's It's not so clear now.
Yeah, this large is from 2 to 8, right?
Yeah, 8. Yeah, right. But as we yeah, so far it's not known why it is the case. But it will give you correct TMD result if you after the perturbation matching. So it is expected. In other words, it is expected from the perturbation matching. The perturbation matching is also not so strong dependent. So then we do the Fourier transform, and you can see the Coulomb gauge case for different momentum here. You have a good signal, and you also have a very stable shape. For the gauge-invariant case, it's very unstable, and the error, if you compare ample to ample, the error is also larger. Then we can, from this quasi-TMD wave function, we can extract the so-called Collins-Soper kernel or the repeatedly evolution kernel by the evolution of the quasi-TMD wave function. We basically use the wave function with different momentum to construct the ratio and with perturbation correction to derive this MS power Collins-Soper kernel. Currently, we use the perturbation correction at the next leading logarithm, and we have the power correction that is surprised by the momentum and also surprised by the transverse separation. Both the quasi-TMD wave function and the perturbation matching kernel depend on the x and the momentum. So the Collins-Soper kernel, if we derive it correctly, it should be independent of the momentum and the x. And it's only a function of vt. And as you can see from these two figures, we show the Collins-Soper kernel derived from different momentum combination and different x. For the large VT region, the part is a different combination overlap with each other, and you have a very stable plateau of this Collins-Soper kernel. It means in this region, the power correction are well surprised. But for the small VT, the TMD factorization does not work very well, especially for when the momentum is small. So you observe some deviation between the different momentum combinations. So this verifies the factorization. Finally, let me just present to you our final result of the Collins-Soper kernel derived from our calculation of quasi-TMD wave function. So as we have seen the gauge-invariant case, the gauge-invariant, both the gauge-invariant result and the Coulomb gauge result, they agree with each other at a short distance, smaller than 0.4 for me. But beyond that, the gauge-invariant case error just blow up, don't give us any meaningful result. But the Coulomb gauge case, we still have reasonable signal up to beyond 0.8 for me. And our result is compatible at a short distance, compatible from the perturbation calculation, as what you have mentioned. So for the small BT, we can calculate from the perturbation theory. But for the large BT, you have to extract it from experiments or calculate it non-perturbatively somehow. And large distance, we also compare with a recent global analysis of the experimental data, and we find a good agreement, and we favor actually a near linear dependence of the beeper.
Just a question. So here for the Coulomb gauge case, is the systematic error also included for the small B Earth region? You just mentioned
right.
For that there's kind of
yes, the systematic is also included. The systematic errors come from, so we have the Collins-Soper kernel is independent of x and momentum, right? But we have several different momentum and x. We just average them, and their deviation is a systematic error.
Okay. Does the same thing include also for the gauge-invariant case?
Yeah, both cases. So that's why even that small BT you have a good signal, but the errors appear to be larger because the systematic errors are larger. So the errors here include both systematic and the statistical errors. Okay, that's finished my talk. So there, in the past few years, there have been many progress in computing the Parton distributions under the framework of effect theory, and there are some difficulties and complexities in the conventional method, and we are come up with the Coulomb gauge approaches and demonstrate the universality in the lattice effect theory through the equivalence of the Coulomb gauge and gauge-invariant approaches. The Coulomb gauge correlator shows advantages of the absence of linear divergence from the Wilson line and enhanced long-range precision. With this advantage, we are able to extract the non-perturbative Collins-Soper kernel from the quasi-TMD wave function in the Coulomb gauge, which appear to be consistent with recent formatization of experimental data. The Coulomb gauge method could also have broader use in the future, particularly in the non-perturbative regime of the TMD physics, also including the gluon TMDs and the Wigner distributions. That concludes my talk. Thank you.
Thanks for the excellent talk. You have a question?
So can you buy one slide? I mean, this is a very nice result. I mean, last year I remember in the workshop, I basic comment, so we don't need lattice because at that time, so you only have the first 3 data points.
Yeah.
And the phenomenology actually very nice result from all the groups, give you a consistent result. I mean, which was against my original motivation to push for TMD 10 years ago. At that time, we said that we need a lattice calculation to get this Collins-Soper kernel because at that time, 10 years ago, the phenomenology application totally different. So they were like all over the place. But I think after 10 years now, if we have all the phenomenology work at next leading law, that's very important because you just need work on the next leading law. The Collins-Soper kernel will be totally different. So that's one of our fix previously will just double this actually. So
okay.
But the lattice is actually very nice and
yeah.
So I have a question. So you mentioned about when you choose Coulomb gauge, you get a light bulb.
Yeah.
Right. Which direction?
It didn't specify the direction, so it's basically a principal values prescription, average over the 2 directions.
So that means that you cannot get the Siebert's function.
So you cannot get currently cannot get the time old TMDs. Okay. Only have time even TMDs.
So if I may have another question, so you showed this comparison to the pion this PDF.
Yeah.
Between Coulomb gauge and HIT seminar.
Right.
I mean, from this comparison, you cannot see the advantage of the Coulomb gauge choice.
Right.
Right. So I guess you came the result obtained coming from same configuration you generated, right?
Mm-hmm.
It's the same lattice configuration.
Yeah. Right.
So looks like there's no advantage.
Yeah, for the PDF case, actually, indeed, we don't want to say too much. Actually, for the PDF case, it's not so important because even we have this issue at long distance, the long distance is not so important. We'll only compute with small x, right? So it's really matters maybe this range of the data, so it's fine. But for the TMD case, it's indeed very important because TMD for any z you have a very long with link.
Yeah. That's good. Thank you.
At some point, you had said that the pion mass was 300 for these
studies. For this PDF test assessment study, it's 300 MeV. But for the Collins-Soper kernel calculation, we have used the minimal calculation with a very large volume and critical time mass.
One more question.
For this Soper Collins, this function you have extract. So you said the last part.
Mm-hmm.
Yeah. So you mentioned the experiment data. Which are what are the experiments? What kind of experiment are you talking about? Is it Drayen?
Drayen semi
It's feed into Drayen.
Drayen cities for Drayen cities.
What?
Semi-inclusive DNS. and Xiang.
Semi-inclusive guys. So these are the
bands.
The band.
Right. They use different parameterizations. You have to use some parameterizations to get the data.
So mainly gradient. So it's basically
Does it
gradient.
include gradient?
What? So there's Z-boson production and lepton and fixed targets.
Okay, so this is like gradient, right?
Yeah, gradient, mainly gradient. What? So maybe I just add a small comment. So I know one of these fit IFY, right?
Mm-hmm.
So they are used quadratic B for dependence.
Yeah, right.
So in our previous fit we have logarithms. So logarithms is similar to linear, I think.
Yeah, right.
So
yeah, this also depends on the B star you choose. So if you use a very large B star, the drop will come very
That's
big.
right. I mean here compared to B star, this is still small b.
Yeah.
In some sense, because B star normally choose like a 1.5, right? 1.5. So yeah, okay, around B star actually.
Yeah, actually we can we can have the very long B perp, but we simply did not save the data because we didn't expect the data have to the signal as this. So as you can see here, our data have a B perp of 8, 10, 8, still have good signal. We can do 28, no problem, but we can simply did not compute it at the beginning.
Okay.
More questions?
Just a possibility. Is there any other better gauge that even better than Coulomb gauge in the future?
Dicom gauge.
Yeah, that's something. The Coulomb gauge, you have some problem, right? So there are some problems we need to solve. So firstly, the going beyond the one loop is also difficult for Coulomb gauge. If there is some choice, maybe it's easier to compute the two loop calculation. And the grid bob copy is definitely something we need to decide.
So the other configuration is the one that you used to do the continuum, the one that you showed in the beginning. Which configurations are these? This is Wilson fermions?
Oh, this one are Wilson-Clover on the HIT.
Okay, so these are milk ensembles, and you put Wilson-Clover on the valence.
Yes, Wilson-Clover on the valence.
Okay, thank you.
More questions? Okay, maybe if no more questions, thanks Xiang again. And Xiang will be here this week. If you want to discuss, just a little bit here on this.
So,